toric algebra and its application. So,
Thank you very much. So I will, does it work like this? So I have this. Maybe it's muted, huh? Yes. Hello, hello. It's working? Doesn't sound different. Put it here more. Hello, hello. Yeah. Yeah, I think so. Hello, hello. Hello, hello. 1, 2, 3. Mark of places. Hello, hello. Yeah, I think now it's there's some effect of it. Okay, so today I'm going to talk about Markov bases, which is the combinatorial version of the generators of the toric ideal we have been talking about yesterday. So I will continue to use my notation. So we'll have still A be one of these matrices that will define a toric ideal of format D times N with integer entries. And I'm going to make a definition of an object that interests me. That's called the fiber. It's the preimage of a preimage of some element in Z to the D under A, but restricted to the non-negative orthant. So let me show you the fiber of B in Z to the D is, so I use A inverse to signal pre-image, but it's the pre-image as a set. And then I use, I mean, it has been tradition somehow to use these square brackets to indicate that it's somehow different, that the pre-image is taken in the non-negative orthant of Z to the N. So that's the U in N to the N such that AU equals B. So let me give you some intuition. So if you replace everything with real numbers here, so this is the set of integer points in the polytope or polyhedron. Let's be more precise. Polyhedron, well, defined by the same. So there's an inequality hidden. So here hidden is the inequality U is non-negative, and there's a linear condition here. So there's a polyhedron consisting of all x in Rn such that Ax equals B and x is non-negative. So by some gadget called slack variables, any polyhedron can be brought into this form. So you know a polyhedron is something that's defined by linear inequalities maybe, and using some extra variables, you can always bring it into the form that the inequalities are only non-negativities and some linear equations. So it might be unbounded, but if this A leads to a homogeneous ideal, so if it has this all ones vector in the row space, a condition that we saw yesterday also, if 1, 1, 1, 1, 1 in row space of A, then all fibers are bound finite. All fibers are finite. And so the picture you could have in mind is a polyhedron that looks like this. And then, so the all ones vector is orthogonal to that space. And you take the integer points in that set. So why would you be interested in that set maybe? So maybe you're interested in that set because you do discrete optimization or combinatorial optimization, integer programming. These are all related concepts. So in integer programming, you optimize a linear function over the integer points in a polytope, say. That's the goal of integer optimization. And you might be interested in that as your domain of your optimization problem. So the way this entered algebraic statistics, so we're going to see a connection of this to the whole story of toric ideals in this Diaconis-Stofels theorem, which follows later. But the connection to algebraic statistics is the so-called Fisher's exact test. Now, I have to shorten the story a bit, so I will tell it to you verbally. And then there's a nice little book you can read about this Fisher's exact test. So Fisher is this statistician who invented many of the fundamental concepts of frequentist statistics that we use today. And the story goes that in the 1930s, 20s, 30s, when Fisher worked with various natural scientists, he talked to a phycologist, Muriel Bristol, and I didn't know what a phycologist was before looking it up. Who knows what a phycologist investigates? So on Wikipedia, it says phycologist investigates algae. So the green stuff that grows in the sea. Is it called algae? Okay. So the phycologist Muriel Bristol claimed that she could taste when the Englishmen prepare their tea, they're pouring milk and tea in the cup, and she claimed that she could taste whether the milk was poured first or the tea was poured first. So Fisher designed this experiment where she would taste 8 cups of tea, and 4 were prepared in one way, 4 were prepared in the other way. And he wanted to test the hypothesis that she's just guessing versus the alternative that she has some means to taste which thing was poured first. So, and then there's some statistics. So this is the beginning of a field of statistical inference that we call hypothesis testing. It goes like this: you make a hypothesis about the random process that generates your data. So the hypothesis that Fisher would make is the lady is just guessing. Muriel Bristol is just guessing. So then you would draw conclusions that would follow from that hypothesis about the data that you're observing. So now you observe the data and you ask, how far is that? Does that data provide evidence against my hypothesis? If the hypothesis was true, would the data that I see be very rare data? Would that be a very strange event given my hypothesis? And if that's the case, that would present evidence against the hypothesis. So with the statistical methods, it's a bit, the idea is a bit like a contradiction proof. So you make a hypothesis, you prove, you show that something happened that's very unlikely, and then you can draw 2 conclusions. Either you conclude, okay, I got very unlucky, something like very rare happened, or maybe the hypothesis was wrong. Okay, and so in this, so now I'm cutting everything short. In this thing Fisher needed to evaluate a certain function on such a set, on such a fiber. So the U's in here were the possible outcomes of the experiment, a little table. So there were 4 entries in this U. Tea was poured first, milk was poured first. She guessed tea was poured first. She guessed milk was poured first. So a little 2 times 2 table is the U. And this map A computes the row sums and the column sums because these were known. So the Muriel Bristol knew that there were 4 cups of each type. So she would also guess that there are 4 cups of each type. So it was known that when you sum over her guesses, she would guess 4 times one thing, 4 times the other thing. And it was also, the preparation was under the same hypothesis. And so Fisher needed to evaluate a certain function on all of these points. So lucky for Fisher, this fiber in his case was very small. I think, I don't remember, I think it has 6 entries or so. And he could enumerate them. Carlos knows how many.
5 tables.
5 tables, okay. In practice, if you look at any matrix that comes up in integer programming or in larger applications of this Fisher's exact test, so this was developed on a toy example, but you could run this on other models, more complicated models, and for other of these values, these things become a lot larger. So problem in applications. Maybe you want to evaluate some function on many points, all or at least many or representative, a sample points of this fiber for maybe unknown B. Unknown in the beginning, before you run this method, unknown B. And this A inverse B can be very large. Very large. So there's a curse of dimensionality maybe. So if the dimension of this polytope is more than 1 or 2, of course the number of lattice points grows intuitively like a polynomial of the degree of the dimension. So back in Fisher's time, there was no solution to this problem except to not apply the method when this is large. But today we have computers. And so in the 21st century, Diaconis and Sturmfeld showed a method that allows you to sample from the fiber. So in modern times, Diaconis and Sturmfeld showed a method to sample points from the fiber. Oh, I forgot to mention the book I wanted to mention. With, well, almost any distribution you want. Okay, so let me just mention this. There's a popular science book called The Lady Tasting Tea about this whole story with the tea and the invention. So, I mean, it's really fundamental. So I think Fisher wrote a book, The Design of Experiments, as a textbook in the 1930s. And several foundational statistical methods are grounded in this book, first time explained in this book, like hypothesis testing, this whole method of assuming something, drawing conclusions from the assumption, and then trying to refute it using data. And also the principle of randomization, of carrying out an experiment under randomized conditions so that it be most informative about the unknown distribution. So these fundamental principles of statistics come from that book. So, and this new book, The Lady Tasting Tea, explains the history of statistics along this story. I mean, it's a couple of years since I've read it, but I have, I just remember I liked it. I don't remember its details, but I remember I liked it. Okay, so so the idea to do this, so what would Fisher do if he had known about this method? So you want to evaluate some function on every of the integer points to carry out the comparison. So in the Fisher test, this function would be a certain distance, or how rare was this data compared to the data that we would expect under the hypothesis. So the points in this polytope would correspond to fake data, other data that would lead to the same estimate. So there's the actual data and it leads to some estimate. And then to see whether the hypothesis might be true or not true, you compare the estimate using the hypothesis to the data you observed and you get a distance. Say the distance is 5. But now you ask, what is 5? How good is 5? So the idea is to generate fake data, generate other data that leads to the same estimate and see what the other data, what distances the other data gets. Okay, so and all the fake data that leads to the same estimate are the other integer points in this set. So what Fisher would have been content with is to get a representative sample of the other points. So if the fiber is too large, it would also suffice to get random, say uniformly random sample and compare it to a large enough uniform random sample of other data that would lead to the same estimate to get an intuition of how rare your actual data is to carry out this test. So what the idea now is to run a Markov chain, a random walk on the points of this in this polytope. So idea, use MCMC, which is short for Markov chain Monte Carlo. It's a certain class of algorithms to construct Markov chains on objects like the lattice points there. Run a Markov chain on A inverse of B, the fiber, to sample from it. So you somehow construct a random walk that walks around here randomly on the fiber, and you let it run for a long time, and then you are at some point and you say, that's my sample. Then you let it run again, you're at some point, and you let it my sample. So what we need for this is some elementary moves. Yeah. So this random walk, when it is at a position, it should somehow do some computation that tells it to move in that direction or move in some other direction. And that thing should connect the fiber. So it should be possible to reach every point. And it should also satisfy the necessary conditions that are known from Markov chain theory for it to have a stationary distribution, to converge to a stationary distribution from which we then sample. And a Markov basis is the set of moves that is used to construct this random walk. Okay. Set of moves for this random walk. So these are integer points, non-negative integer points. Moving from one to the other is going to be a point which can have negative coordinates. And so you want to stay. So all points in the fiber have the same image under U. So these under A. So these elementary moves will be in the kernel of A. Yeah. So it's going to be a subset of the kernel of A. So, and we've seen the kernel of A yesterday. So these correspond to binomials, we already know. And that's the fundamental principle here. Okay, so let me make the definition first. A set M, like Markov, in kernel C of A. Maybe we want finite, let's say finite, is a Markov basis. For A, if two properties hold for any B. So there's one Markov basis for that works for any B if for any B and any UV in the fiber for this B, this arbitrary B, you can construct a chain that goes from U to V using only the moves in M, and you add them or subtract them. There exist M moves M1 to MS in M or maybe minus M, such that you get from U to V, U plus all the moves applied, I from 1 to S, Mi is equal to V. You get from U to V by adding these moves. But you should not, while you're doing that, leave this fiber. If you're walking out of the fiber, you will have difficulties proving that this converges to a stationary distribution, the Markov chain that you construct from this. So the restriction that we're going to make is that whenever, during this entire process of adding one move at a time, I always stay non-negative.
What do you mean by moves between points? Is it a path between points or something else?
Yeah, so, okay. I have U in the fiber, and I add M in this integer kernel. Then I call M a move because it's the sum. Okay. AU plus M is AU plus AM. So it's AU plus 0. So this linear condition that we have on the fiber is always still satisfied. It doesn't change by adding these elements of the kernel. And that's I call them moves because of this application. Yeah, so you move from one point in the fiber to another point in the fiber by adding one of these moves. But
translation. What kind of translation?
Translation could also be said, maybe. Yes, okay, I don't use translation, but it is adding something in the code. Okay, but what could happen is that you move out of the non-negative orphan, of course. Yeah, and we don't want to allow that. So my second condition is that I find all this M1 to MS such that any intermediate sum here, U plus some I from 1 to some other letter T, Mi is non-negative for all T from 1 to S. So this here ensures connectedness. And this one here ensures convergence. So you have to trust me that people who study Markov chains and study computational properties of Markov chains will, given this, know how to construct an algorithm. So the one simple algorithm is the Metropolis-Hastings algorithm. I can briefly sketch it. When you are at one of these points and you want to construct the next step, you're gonna pick one of the elements in the Markov basis uniformly at random. You're gonna check if when you add that move, you're gonna leave the fiber or not. Check this condition here. And if you leave the fiber, you reject that move. If you don't leave the fiber, then you might still reject that move with the probability of epsilon. You still reject that move and draw another one. And with the probability of 1 minus epsilon, you just apply that move and start again at the new point. And then you, by tweaking that rejection probability, depending on something you compute at the point, you can make it so that the stationary distribution is basically what you want. Just by tweaking, this is one of the insights of this algorithm, is that by tweaking this rejection probability with which you reject otherwise valid move, you can get to any distribution you want. And Fisher would like a certain hypergeometric distribution, or maybe your uniform distribution is something good to think about. Yeah, if you maybe want to just sample points from this large set, you use uniform distribution. Okay, so this is something that people studied. Of course, there's the whole Markov chain story now. So the question, when have I achieved the stationary distribution? So if I want to use this as sample, I let it run for 300,000 steps. But again, how good is 300,000? This is the analysis of mixing times. So the mixing time of a Markov chain is the time until you are close enough to the stationary distribution to say that I've run for 300,000 steps. So maybe what I have now is a random point. But it depends very much on the properties of this set of moves. So if you draw in all the moves that are possible at each of these vertices, you get a graph on this fiber. And so the connectivity properties of this graph can be very, very bad. For instance, this graph, so my former PhD student, Tobias Windisch, has studied this in detail, and he constructed examples in which these Markov chains look like this. So there's a large Kn, a complete graph here, one edge, and a complete graph here. And you can make n arbitrarily large. So this is as bad as it gets for Markov chains. So for a Markov chain, this essentially looks like not connected. So it's going to run around in the Kn here all the time. And then there's one position where there's a small chance that it moves to the other component and it stays there forever. So this running a Markov chain on this will have like very bad mixing properties, and this can happen. Yeah. So this is kind of a experimental science that the physicists have perfected to just look at the run of the Markov chain and see if it has converged to stationary or not. Okay, it's also something you can read Tobias' paper. He also speculates a bit about how realistic such a thing is. So for Fisher, this does not happen. Okay, so we have done this. Okay, so now you're convinced you want a Markov basis, but why should a Markov basis even exist? So if I put finite here, so it should be the same Markov basis for all B, yeah? So A is fixed, it's the Markov basis for A, but B is arbitrary. So it should be the same set that connects all the fibers for any B. So why should a finite Markov basis even exist? Why should finite Markov basis even exist? So one works for all B. So at this point, I can make the joke that Emmy Noether proved that finite Markov bases exist. Because in the end, using this Diaconis-Sturmfeld theorem that I'm going to present next, it goes back to the fundamental finiteness properties in commutative algebra, that ideals are finitely generated in the polynomial ring. So the Diaconis-Sturmfeld theorem, some people call it the fundamental theorem of Markov bases, says that finding a Markov basis is the same as finding a finite generating set of the toric ideal corresponding to this matrix A. And the correspondence is, of course, that the elements in the Markov basis are the exponents of the binomials that are the finite generating set. As set M in the integer kernel of A is a Markov basis if and only if the toric ideal IA from yesterday is generated by the binomials, the finitely many binomials that correspond to this M. So x to the M plus minus x to the M minus for M in our set M. So this is let's be super explicit. This is the toric ideal of A from yesterday. Okay, so now we're very interested in explicitly computing generators of toric ideals. So I think this is a good example. Good example for why applied mathematics sometimes gives you new ways to think about things that you know for 100 years. So I think ideal generators in Emmy Noether's times were not of high interest. So you have it, the fundamental object is the ideal. The fundamental object is the vector space. And picking a basis is making choices. Picking ideal generators is making choices. So if you talk about the mathematical objects, you don't want to make arbitrary choices, or only if you're forced to do it. And then later you want to show that whatever you do is independent of your choices. If you think about just basic vector space theory, okay, so the definition of dimension is you take the cardinality of a basis, but then you essentially prove that it doesn't depend on the basis. All the bases have the same cardinality, and it's a useful definition, this cardinality of a basis. And so in the old days, you would think about generators as something you pick if you do a calculation. But now there's this explicit reason to actually compute generating sets. And some generating sets might be better. Some generating sets might be worse. Yes, in terms of the connectivity properties of this Markov chain, it might make a big difference which Markov basis is used. So now suddenly you could ask about uniqueness. Is this generating set unique? What are uniqueness properties? So new algebraic questions that were just not deemed interesting can become interesting sometimes by looking at it from a different perspective. So the uniqueness question is interesting. So I just tell you the answer. The Markov basis is of course not unique, but you need to, there are some specific fibers that you need to connect. So the Markov basis needs to connect all the fibers, but there is a unique, well-defined, depending only on a set of fibers, so that when these finitely many fibers are connected, all the fibers are connected. And this is an invariant. So this is like any minimal Markov basis needs to minimally connect these specific fibers, and you can compute them with homological methods or computer algebra methods. There are different ways to get to them. Okay, so an idea about the proof. The proof is not so complicated. Maybe just a brief idea. Okay, very brief idea. Idea of proof. So if you have your chain U and V, and now I'm going. So you start from U, you apply the first move and you get to U1, then you apply the second move. So this is M1. You apply the second move to go to U2. So then you want to write in terms of binomials, x to the U equals how do I want to write it? X to the U minus x to the U1 plus x to the U1 minus x to the U2, and so on. Okay, this will be, it will end x to the U minus x to the V. It will be ending with minus x to the V. And now so I just input, I take x to the U minus x to the V, I input many zeros and write the zeros as these differences. But now I observe that from U to U1, I applied one of these Markov moves. So this thing is of the form x to the some monomial W times one of these Markov moves, x to the M1 plus minus x to the M1 minus. So that's in the ideal. Yeah, I think that's the basic idea. Making these expansions, you write your change from the one lattice during the walk. When you go from one lattice point to the next, you're applying this move, and applying this move is finding M1 in the first monomial, factoring out what remains and replacing the part that is in M1 by the plus by the part that is in M1 minus. Okay, so then computation. Okay, now you want to know Markov basis, so you fire up your computer algebra system, so you can compute the kernel like we did yesterday. First idea, compute kernel of phi A with generic kernel methods. So who knows what Macaulay 2 does? It does something. You type kernel and out comes the kernel. It does some Gröbner basis methods. So this is slow, comparatively slow. So a better approach has been to use so-called saturation. Use saturation. So it goes like this. You start with a lattice basis. Let L1 to LS be a lattice basis of the integer kernel. This is easy to get. Yes, this is linear algebra. Linear algebra is easy. Linear algebra over the integers. It's at most, it's also few vectors. So these Markov bases can also get very large. Yeah. So they're much more necessary than the codimension of the ideal also. But this lattice basis is comparatively small. It's at most n elements, and we can easily compute it. So we can make the ideal corresponding to this. So let I prime be the ideal corresponding to this. Li plus minus x to the Li minus for I from 1 to S. So that's too small, yes? All of these binomials will be in the toric ideal, but generally this is a too small ideal. And then it holds that if you take I prime and you compute the colon ideal, or some people call it saturation, with respect to all the variables. So I will explain this a bit more. Maybe it's known to the people studying commutative algebra. And so this is equal to IA. Okay, here. Okay, so what is this? This is just the product of all the variables. Ignore this infinity, yeah? So the notation written is you take this ideal I prime, colon, and then a specific product of the variables. Forget about the infinity for a second. So I'm going to define this. I prime colon f, if f is some polynomial, is all the things that are multiplied into I prime by f. So it's the g in kx such that gf in I prime. So it's larger, potentially larger than I prime. Yeah, because I can multiply anything that's already in I prime with 1, and there you go. So what you do here now is you take the product of all the variables. That means if you find something that's divisible by one variable, you put in that something divided by that variable. Yeah. So if you find x to the w, x to the u minus x to the v in I prime, it implies that x to the u minus x to the v in I prime colon this product I from 1 to n xi. Oh, I haven't explained the infinity. Okay, now infinity just means you keep doing that until it stops. It's a Noetherian ring. It becomes like larger and larger. Potentially at some point it stops because it's a Noetherian ring. You can't have infinite ascending chain. So I colon f colon f colon f colon f. until it stops growing. That's the definition of I colon f to the infinity. And that means you can divide by any monomial. Yeah, if you see something that's a monomial times something in the ideal, you can divide by the monomial. And doing that gives you IA, and that can be implemented very efficiently. So this saturation is implemented efficiently in a program called 4T2. Number 4 TI2. I can show you in the tutorial this afternoon. Okay, so once this was settled and we could compute many Markov bases, people have done that, and hundreds of Markov bases have been computed. Yeah, so now there was sufficient motivation to get these, and now happens this what I already outlined yesterday. People input their favorite matrix A from combinatorics into this method, see what they get, try to understand how it depends on operations you can do on A. And I'm going to show you a more interesting example of such a Markov basis now, and it's connected to independence, what Carlos introduced yesterday. But we're going to do only the unconditional independence. Okay, so some literature. There is now a textbook called Markov basis in algebraic statistics, I think. I didn't print the title of the book. It's cited in these notes, and it has the accumulated insight that was generated from running this program 42 a lot. And I think this is also an interesting research data story. So in Germany, we have now a big discussion about research data and how to make research data what is called fair. Fair stands for findable, accessible, interoperable, and reproducible. And so this was an early, there was an early example of nice research data in mathematics. Together, when we were PhD students, Johannes Rau and I used this program a lot, and we just put our examples that we computed up on a website. It's called markovbasis.de. It's still up. The design looks a bit like 2008, but it's still working. And when you have hundreds of examples, so this is this mechanism that I explained yesterday. You have a graph. To the graph, you associate a matrix A. To the matrix A, you associate these generators, and then you ask, how does the degree depend on properties of the graph? And once you have the data, you can run all sorts of analysis on these examples. And some of the examples we have in our database, the computation still took like 2 weeks. Yeah, so it's good to just have a table where the computation that takes 2 weeks is done, pre-done. Yeah, and then we wrote scripts that just automatically go through classes of graphs or classes that we found interesting. Okay, so let's be a little more specific in this example of the independence model. Example of independence of two random variables, And okay, Carlos used normal distribution. I will use discrete distribution. So x1, x2, both finite. Let's say x1 takes values r different values. So this is my notation for the first r integers without 0. And x2 takes s. So what is a joint distribution? So if you talk independence, is always a property of the joint distribution of several variables. So we're going to take the very short vector x1, x2, and a joint distribution. The best data structure for this is just the probabilities, the elementary probabilities. Pij, which is the probability that x1 comes out as I and x2 comes out as j. They're just numbers. R times S numbers. So this is non-negative. Yeah, so I from 1 to R, J from 1 to S. Pij is non-negative and sum is 1. Yeah, elementary. That's the data structure for elementary for such a distribution, just the elementary probabilities. And I think of it as a matrix. Yeah, it's good. It has 2 indices. It's good to think about it as a matrix. So, and then it holds that x1 is independent of x2 unconditionally if and only if this distribution factors. So Carlos had this definition of independence as the density factors, and working through the example, you see that it's the same phenomenon. This matrix factors as the product of 2 vectors. When you take the product of 2 vectors, you can do it one way, it gives you a number. The other way, it gives you a rank 1 matrix. And this is the other way. So if this matrix factors, and in fact, it factors into the marginals in this simple case, if and only if Pij equals Pi plus times P plus J, where Pi plus is equal to the sum over J Pij, and P plus J is the sum over I Pij. So if I have my matrix P11 to PRS, then Pi plus, these are the row sums. I sum over the column indices, so I sum along the first row. P1 plus is the sum over the first row. If I sum in this direction, I get P1 plus. And if I sum in this direction, I sum over, so this plus indicates sum over this index. So here the sum would be P plus 1, and it goes to P plus S. So these are called the marginals or the row sums and column sums. So in the independence model, all Pij under which x1 is independent of x2 form the independence model, which is an algebraic variety. That's one of the mantras of algebraic statistics. Statistical models are algebraic varieties. So that's a statistical model. Yeah, statistical model in algebraic statistics is a set of distributions, like the ones that are independent, the ones under which x1 and x2 are independent, and that it forms a variety. Maybe it's not so obvious yet, but you should think of this as a monomial parametrization as we had it yesterday. So this says the xij is given by one of the t's times another of the t's. So just accept that these things are called p's now. So let me spell it out in a little lemma. X1 is independent of x2 if and only if the matrix P that has these Pij entries is of rank 1. And then you know the criterion from linear algebra, hopefully. This happens if and only if all the 2x2 minors, all 2x2 subdeterminants, I call them minors, people call them minors, all the 2x2 minors of P vanish, and that is a toric variety. Such P form part of a toric variety. Okay, so what is obvious. So this is writing the matrix as vector times vector in the wrong way. Yeah, vector times vector. And if a matrix is of the form vector times vector, all of the columns are obviously linearly dependent because they're all just like multiples of each other with the coefficients that are in the other vector. That's why it's a rank 1 matrix. Yeah. So all the columns are dependent. Same argument, all the rows are dependent. Then there's this linear algebra characterization that a matrix is rank 1 if and only if, I mean, even more, it's the rank R if and only if all the R plus 1 times R plus 1 subdeterminants vanish. So in this case, it's the 2 by 2 subdeterminants, and the 2 by 2 subdeterminants are binomials. If it was rank 2, we wouldn't be talking about binomial ideals at all, but here we're talking about binomial ideals. So that's good for us. And yeah, that's the toric variety. So let me give you the simplest example. If R equals S equals 2, you have 2 binary random variables. So that's a 2 by 2 matrix. Then ideal of x1 is independent of x2 is generated by P11, P22 minus P12, P21 by 1 2 by 2 minor. So that's the case of a 2 by 2 matrix, and there's only one of these minors, and that generates it. And I brought you the realization of this, which I 3D printed at home. So this is how it looks. So I did it. We're in 4 space because we have P11, P12, P21, P22, but the sum of the coordinates is 1. So that's why we're in 3 space. So the set of all distributions is a simplex in 3 space. It's all the 2 by 2 matrices with non-negative entries whose coordinate sums to 1 is this tetrahedron. Okay, inside that tetrahedron, you have a, turns out, 2-dimensional set, yeah, 1 equation, codimension 1, 3-dimensional tetrahedron, 2-dimensional set of independent distributions, which, yeah, looks like this. It's a truly, I put it on the table, you can look at it. It's a truly 3-dimensional experience. It's really hard to take a good picture of this. So the way I memorize it, it's a square. You take a square and you bend it so that it sits inside this tetrahedron. Yeah, so the 4 edges of the square run along the edges of the tetrahedron like this. It's also a ruled surface, so it's a union of lines, which, I mean, starts from the edges and then moves. You look at it. It's a 3-dimensional experience, and this is very much known. It's also known in projective geometry. So this construction is also known as the Segre embedding in projective geometry, where you embed a product of projective spaces into a higher dimensional projective space. So this is the case of embedding P1 times P1 and P3. Okay, yeah, what else to say? The Markov basis. Okay, so we read the Markov basis from the exponents of these binomials. So this is a little plus minus pattern with 4 entries. So Markov basis. So this A for the independence model. So now you can ask, what's the A? I haven't been talking about the A. So A turns out to be this matrix that computes the row and column sums. A is the linear map that computes row and column sums. And you need to twist your head a little, because now the U, we do AU equals B, the U is a matrix. Okay, so, and the row sums and column sums are 2 vectors, so you have to think of the matrix as a vector and put the U and the row sums and column sums in one big vector. But I think you can deal with it. So e.g. in the 2x2 example, let me show you one way how to do this. 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. So if I apply this to U11, U12, U21, U22, I get the row sums and column sums. Oh, maybe I should do this the other way around for the full symmetry. 0, 1, 0, 1. I get U. Okay, this plus this. This is U1 plus U2 plus U plus 1 U plus 2. This is like 4 and 4 is like because of this small example. You should think of this as gigantic and this thing as short. Yeah. So this matrix still has codimension 1. There's one row too many, but therefore we have the symmetry. So it's fine. And so the Markov basis consists of moves that are of the form plus, minus, minus, plus. And this is applied in any I1, I2, J1, J2 for any choice of rows I1, I2 and columns J1, J2. So what this says is that when you have two tables, if U11 to URS and V11 to VRS have same row and column sums, they can be connected by making only these plus, minus, minus, plus modifications. Yeah, you start from this table and then you maybe you pick I1 and I2, J1, J2 to make them closer in some metric. Yeah, so maybe U11 is 5 and here it's 4. So you apply, the first thing you apply is minus this thing. Yeah, of course, also minus this thing. There was a minus in the Markov basis. You subtract 1 here, add 1 here, add 1 here, subtract 1 here, and then they become close. And it's a good combinatorial puzzle to figure out what's an algorithm, what's the optimal strategy to go, what's the shortest path from one way, from one table to the other. Or to directly prove this property without using the fundamental theorem. If I just give you this combinatorial puzzle, okay, you have these plus minus moves that you can apply in any two rows, any two columns, and you have two tables with the same row sums and column sums, show that there always exists a path. Yeah. So Seth Sullivan invented the tableau notation for this, but I'm not going to take it away from you to figure out this puzzle yourself. Okay, do I need to erase something? Maybe I make the last comments verbally. So this is only the very beginning. So now you ask, what are the hundreds of Markov bases that are in Markov bases you find on a markovbases.de? So now what people have been doing is to construct many of these matrices. So here there's a uniform answer for arbitrary R and S. If R and S grow, the number of moves grows because I have all these rows and columns to choose from. But structurally, nothing changes. It's always this plus minus pattern, or to say it differently, it's always generated in degree 2. If R and S grow, the idea is always generated in degree 2. Now, the next simplest model, one could say, consists of 3 variables. And you compute the margins for any set of two variables. So here I had two variables and I compute the row sums and column sums. Now think about a three-dimensional tensor, if you wish, where I compute the margins are the three matrices that arise by summing over one of the dimensions. Okay, I can do the whole setup. I can do the linear map that computes from a three-way tensor, the three two-way marginals, and I can compute the toric ideal for that tensor. If it's like, if I do 2 by 2 by 2, it's generated in degree 4. And as soon as I let the R and S and T, now the dimension of this tensor, grow, the degree will grow. And it will be, there is a universality theorem that says already in this simple model, it can get as bad as it gets. So letting these R and S and T grow can be pretty bad. But then people have also, people have focused more on the side of changing this structure of what are the variables and which marginals I compute. And one way to store this data is using a simplicial complex. So you have a simplicial complex on n variables, and you compute the marginals for the faces or the facets. It suffices to compute them for the facets. And this is much of the data you will see on markovbasis.de is of this form. Simplicial complex makes a matrix, makes toric ideal, and then gluing theorems for simplicial complexes, and so on and so forth. Okay, thank you very much.
Any question?
Okay, so if there is no question, is there any question from the IBA campus?
So
There are questions on the chat. Okay, sorry. Are there any questions from the online audience? Could you please check?
Can you give a simple example how to get to the toric ideal, the matrix coming from a simplicial complex?
Okay, how to get to from the simplicial complex? Okay, so if delta is a simplicial complex on n, this corresponds to n random variables. And then you would consider the linear map. A that takes in a tensor of order n. So it maps u I1, I2 to In to the marginals for the facets of the complex. So I just do it on one element. Okay, how do I do it? I use an I plus, so you keep the indices that are in the facet and you sum over all the other entries and you do that for all facets. So this is I facet of, F is better, facet of delta. So the independence example that we've been just doing is n equals 2 and the simplicial complex is just the two vertices. Okay, two vertices, no edge between them. The example with the universality that I've been talking about before is the triangle, the empty triangle. So the empty triangle, you would have a 3 tensor and you compute 3 matrices that are two-way marginals. So this is better to do with the computer. So these matrices are huge, of course, and I can show you some in the tutorial session that are generated by computer. But they're all 0-1 matrices, yeah, because it's only summing. There's 0-1 matrices, and combinatorial optimization people have looked at them. Sometimes they know gluing theorems for these combinatorial structures. Yeah.
Are making the multiplication of this matrix 4x4 matrix with the column or below right below?
Yeah.
Is it multiplication or something else?
Yeah, it's multiplication. It's a linear linear map. So doing this summation is like a linear map. So that's the matrix implementing the linear map. So if I do the multiplication, I do this plus this is the first entry. This plus this is the second entry, and this plus this is this. And yeah, matrix product. Linear map as matrix product.
If that the column is same, maybe they can repeat it. What is written in the right column?
U1 plus, U2 plus, U plus 1, U plus 2. This is the notation that I introduced here. If I put a plus instead of some indices, it means to just sum over all the possibilities for these indices.
Is there some process of going back from starting from a matrix and ending up to a simplification complex or something comparative?
Difficult experience, and I mean, it's the question. If you have a 0-1 matrix, is this the incidence matrix of some structure? Yes. You just write the structure, and then you could check if that structure is a simplicial complex. But most often, if you think the whole way, you would start with generators, and then you make the A matrix, then you won't get this nice matrix.
Yeah,
You will get some matrix from which you don't see anything. That's equivalent to the nice matrix, yes?
Is there any other
Question? Okay, if not, so let's thank the speaker.
Okay, now it's very, very fast.
It's because it was a different.
Check out the tetrahedron.